Okay, so let's start. I'm Cecilia Mascia, and he is Giovanni Delussu from Italy, from the CRS4, which we will talk about in a minute. And today, with our presentation, we want to tell you about our experience in using openEHR as a solution for improving the accessibility and the long-term interoperability of a colorectal cancer cohort of BBMRI-ERIC for research. So this is what we will see, very briefly who we are and who is BBMRI-ERIC. And then we will see practically the steps that we perform to move from the original data source to an openEHR-based solution. And then we will see also very quickly an ETL tool that we develop in order to export data from the openEHR-based CDR to FHIR and OMOP formats. So the Center for Advanced Studies, Research and Development in Sardinia, in Italy, is a public research center to which we belong. And our sector, in particular, we deal with research cases in which there are complex and massive data sets, like, for instance, the ones from the biomedical domain, which are mostly focused on. BBMRI-ERIC, on the other hand, is the European research infrastructure for biobanking and biomolecular resource. Basically, it is a big big ecosystem that helps researchers and biobanks to collaborate in giving access to collection of samples and also accessibility to data collection in order to support research. Especially using some of the tools they developed, like the Finder and the Locator, that helps researchers in find reusable resources according to their needs. The colorectal cancer is one of the main, the mostly diagnosed type of cancer worldwide, and for that reason, in 2019, BBMRI collects a big set of data across Europe from 26 biobanks, putting together more than 10,000 cases of patient diagnosed with colorectal cancer. It was a very rich data model because it was made of different clinical data types, phenotypics, so like therapies, clinically relevant biomarkers, procedures, etc. But also it contains other information from digital pathology reports and so on. So it was a very complex data set. In a project which was aimed at improving the accessibility and the interoperability of this cohort, we work on a demonstrator related to the clinical data cloudification. So our goal was to improve the interoperability of this data set, also to support cloud-based data analysis, by leveraging the openEHR characteristics to represent the data set in order to improve the interoperability in the storage and so on. So main motivation of this work lies behind the fact that the original data set, the original collection of data, was stored in a relational database centrally at BBMRI-ERIC capacities. And of course, the ad hoc structure that is behind this repository could be a limitation respect to the data reuse, and also the idea that there is not a semantic rich data model behind that could cause some problem if you want to reuse data productively, let's say. So the idea was to use an openEHR to improve these characteristics. Yeah, this is what is showing the schema is basically the steps that we go through. So starting from the original data set on a relational database, we do in parallel the modeling of the data, and then we work on the actual practical steps that starting from that data set go through the export, pre-processing stages, and the conversion to openEHR composition that were stored finally in an EHR-based CDR. And then in the bottom part, there is also the tool that we developed to extract file resources on one end and OMOP CDM table in order to communicate with the BBMRI-ERIC ecosystem that adopt those standards for some of their tools. Yeah, let's see, let's start with this part, so related to the data modeling. So the process is started with the analysis of the data model. The original data model was formalized in XSD format, so it's what has been performed was to analyze each variable to understand everything behind them, so the semantics, the various constraints, so unit of measure for quantities, possible values assumed, etc., etc. And then on the clinical knowledge manager, we search to find reusable models in order to represent properly the data. And then we do the real data mapping, so the part in which we try to find correspondences between the data nodes from the original data set to the nodes of the archetype. So trying to match everything, so the description, the cardinality, possible terminologies, and so on. So using a free-to-use tool, we do the first design of the model, and then we aggregate the archetype in order to produce the first version of the model, of the template, which is made of 24 archetypes that we select from the CKM. We do not need to develop new ones, so we find almost everything we need. It is organized in 8 sections that reflects the original formalization of the data set. And yeah, the boxes represent simply what we done to personalize and to customize everything. So one thing, the important thing that we do was to bind to external terminology. In particular here, as you see in box C, we use the OMOP standard vocabulary as the terminology. And also in box D, we show how we use the annotations for a double scope, because from the one end, it was useful for automatize the conversion, because we practically add the labels of the original node in the source data set. And then secondly, we see it as a possibility to track the provenance of the data, because it is possible to come back to the original source to understand what data was what data point. Yeah, that's simply the way in which we use the OMOP standard vocabulary. So we look in the browser, that is Athena, to find the proper codes, and we add them in the template, so on the left side, on the compositions. Of course, the codes are within the composition, and it could be also used and useful in making SQL queries to extract specific data from the data set, like we do in the last part of our work. Yeah, so we'll pass to Giovanni for the implementative part.
Okay, now let's see briefly the data processing steps. So we started with the Postgres database with 52 tables, and here each patient has its own unique Postgres ID, and we preserved it throughout the process, the data processing process. And our goal was to extract clinical and genetic data along with an identity lookup table that maps this Postgres unique data ID for the patient with the ID given to the patient by the biobank originally. Using pgadmin and SQL query, we retrieved the data from the database and saved them as CSV files. This is the SQL query with some multiple joins and what the CSV file looks like. A similar process for the lookup table. At the top of the slide, the SQL query that retrieves a JSON field, and at the bottom, an example of a lookup table. Next, we converted the CSV files to the XML, the legacy format Cecilia talked about. The XML file was the original input for the Postgres database, and its documentation was the basis for the creation of our template. This is briefly the structure of the XML. For each patient, we have one basic data section, which is compulsory, and multiple optional events. Basic data so includes standard data such as biological sex or age at diagnosis, but plus diagnostic imaging exams such as computed tomography or magnetic resonance imaging, but also oncogene mutation status markers, and like HER2 or the one in the RAS family, analysis of microsatellite instability and expression of mismatch repair genes. The events, which were optional, were surgery, histopathology sample, then therapies, and response to therapy. They can be instantiated multiple times, apart from histopathology, which is singular. Then we are at the creation decompositions, which was done through a Python code whose main input was the web template itself. The XML files we just saw with the data, the ID lookup table. Optionally, we have a check flag that, when enabled, warns if some leaves are missing, mandatory leaves are missing with respect to the web template. In output, we created a composition, openEHR composition in the flat format, like this one. You can see on the second row the Postgres ID I talked about before, and the third row, the one given by the biobank. Challenges, well, the first one was what should be mandatory in the template, and we decided based on the XML documentation and tested through the conversion. So it was an iterative process. Of course, the enforcement of what is mandatory, it's a problem that depends on what is instantiated. So, for instance, if we have in our data a sample ID, then a material type is required, and vice versa. When required fields were not available, we put in our composition, we created a null flavor value. Another challenge is the multiple occurrences of the same data. For instance, we can have a patient who's had multiple surgeries. We solved it with the use of annotations, not only on leaves, but also on each node whose multiplicity was greater than 1. Then there were some biobanks with quality issues, such as conflicting information in basic data or histopathology. We try to reconcile the discrepancies when possible, and when not, we drop the record or the patient altogether. Then we had to deal with typos, inconsistent capitalization, extra spaces, and different terminology. Sometimes it was challenging. I reported an examples. One biobank had mucinous carcinoma, and we mapped it to mucinous adenocarcinoma. So we had to study on that because the two are synonyms in the context of colorectal cancer, but this would not be the case in other types of cancer, like, for instance, breast cancer. Then we uploaded the composition into an openEHR server. We chose Airbase. At the time, it was in one of the earlier versions with limited validation. So we had the problem that sometimes the composition missed some of the data we inserted. So we created a check, a post-insertion check, retrieving the composition from Airbase and making a comparison and warning the user if some fields were missing or different. Then we performed a consistency check. So we checked if all the data from the XML files were available in the EHRBase compositions, and if so, if there were any difference. Finally, we created a tool that from generic data converts to exports to OMOP, SEDEM, CSV, and FIRE.json formats files. We applied this tool to our CRC cohort data, retrieving with an SQL query those data. This is the SQL query, and the tool uses MyAbyss 2.0 as intermediary classes, as intermediary format, and MyAbyss is the minimum information about biobank data sharing. Is a terminology created by BBMRI-ERIC that describe biobank-related data. And so it was well suited to our data set. So the only thing we had to do was mapping our CRC cohort data to MyAbyss. Then we leveraged the already done mapping to FIRE and OMOP. We created the output files. Those files were inserted into the BBMRI-ERIC federated platform, enabling the researchers to query them. So, in conclusion, we successfully cleansed, ontologically enriched and imported clinical and some genetic data into an openEHR server, and exported a subset of those data in FIRE and OMOP SEDEM for the query in the BBMRI-ERIC federated platform. Future work could include the importing of in-depth genetic data, which has also available for the same cohort, using the archetypes developed in the openEHR genomics project. So this is a little of advertising. There is a poster about it. Tomorrow you can see in the poster session. openEHR meets genomics, join the challenge. Okay, all the work was released open source. Okay, thank you for your attention. Finally, some appropriate acknowledgements and, okay, questions, any questions? Maybe later.
Thank you so much. Questions